Hello and welcome to the University of Plymouth. My name is Richard Pemberton. I'm going to be one of your lecturers here in mechanical and marine engineering design, and I'd like to take you through some of the course details regarding our mechanical, our composites and our marine technology degree programs that we have on offer. This diagram shows how we like our degrees to take you from an entry point on the left of the diagram through our degree program to the right hand side of the diagram, which represents a career in engineering. As you can see on the left, students join our degrees from a wide and diverse range of backgrounds, and the first year, which is combined with our civil and coastal engineering courses, serves to give these mix of backgrounds an opportunity to level out and sets the foundation for the rest of their program through the degree. At the end of the first year, you have the opportunity to confirm your pathway. So you could choose to go down a civil and coastal route if that's something that's interested you while you're here. Alternatively, and the more expected route would be that you'd carry on in the one that you'd applied for, which would be either mechanical engineering with composites, marine technology, or marine technology with composites. But you can choose between that mix of degrees. The second year is where we start introducing program specific content, and we'll cover that a little bit more later on in the video. At the end of the second year, one thing that we really encourage our students to do is to take an optional placement year. We've got a video on that as well, and you'll be able to find that on our website. It gives you a few examples of what students have done in that year. Following that placement year, or continuing straight through from the second year, you've got the third year of the degree program, and this is where we've got more content still that's specific to the pathway that you're on. It's at this point that you've got the decision at the end of the third year whether to continue for an extra year of study, be it the continual progression, which would be onto the BEng, or be it as a separate degree, which would be an MSc, or to leave with the BEng award. You may be wondering what's the difference between these awards, and it's here that we really come on to the right hand end of the diagram with the careers in engineering. The key difference is in how the professional bodies who govern engineering will recognise you as a professional within the engineering industry. Your degree course has been accredited by these professional bodies, and as an individual you can apply for personal accreditation, be it in the form of chartered engineer status or in the form of incorporated engineer status. And the real difference comes is that to be a chartered engineer, the professional bodies want you to have studied at that master's level. What does a chartered engineer do, and how does it differ from an incorporated engineer? Chartered engineer tends to be more of a project manager role, have some sort of financial responsibilities or some project management responsibilities, whereas the incorporated engineer tends to be a bit more of a technical role. Either way, you can have a great career in engineering following either pathway, and we look to get our degrees to cover your chosen route through this. Here are the modules we cover in the first year of our degree program, and we've got another video on the website which goes into a little bit more detail on the subject areas and what each of them means. One of the things you can see is that within our degree program there's a fairly even split between what's examined in a coursework and what's examined in a more examination format. That continues throughout each stage of study. The second year shows where you start to specialise a little bit more depending on the pathway you're on, and you can see that this continues further into the third year of study with more specialisation still. A large chunk of that third year of study is the honours project, and there's a video on that as well detailing some examples of student projects that we've had in the past. The semesters are split with 13 weeks teaching and 2 weeks of assessment, fairly similarly between The first semester going from September to just after Christmas and into January, and the second semester, that varies a little bit depending on the placement of Easter. You can find out more details on our website if you go to plymouth.ac.uk, and you can search for the course that you're interested in, and there it'll have the up-to-date details in terms of entrance requirements. Obviously, with the current situation, we've also got a page which will give you more information on terms of how we're dealing with the coronavirus and how that affects applications. One of the things we'd like to make out, we don't make unconditional offers, but we are always willing to revisit applications in August, so don't panic. Just wait until you've got the confirmed grade. And if you would like to contact us on anything, please do so through the admissions email at plymouth.ac.uk or on the telephone number given below.
Hello and welcome to this video all about some of the subject areas that our engineering students study here at University of Plymouth. My name's Adam Kite. I'm a lecturer here and specialise in engineering design and also computational fluid dynamics. So as I say, I'm going to be talking about some of the subject areas that you might expect to see on your timetable when you come and study here at Plymouth. The way the timetable is structured, you can find out a bit more information about that in our course structure video. And here what I'm going to do is look at some of those subjects that you'll see on your timetable in a little bit more detail. But what I've done is I've put the subjects into context and talked a little bit about them in the context of some of the projects that I discussed, the group projects that I discussed in the projects and dissertations video that you can also have a look at. The two projects in particular that I'll be looking at or using as examples are the human-powered submarine project and the hand cycle project. So these are the sort of things that you might see on your timetable. We'll have a look at them in a bit more detail in turn. So first of all, fluid mechanics. And this is also all about how fluids, whether that may be liquids or gases, behave. So aerodynamics is one particular branch of fluid dynamics. So using the hand cycle as an example here, we have some relatively simple formulas about how a simple shape, this is called a torpedo with a flat tail, this particular shape, some formulas that might predict the aerodynamic drag of something like that. Going on to a shape that's a bit more complicated, a bit more representative of our hand cycle, we can test things in our wind tunnel, so make models and test in the wind tunnel. And we can also use numerical simulation, so computational fluid dynamics, to predict in a virtual environment how the aerodynamics of the device is going to work and produce output like this. In structures, you'll look at the behavior of solid objects. So if it's a simple thing, there's a diagram of a beam that's got some loads on it and some supports. We can again use some fairly simple maths. We can also do experiments to understand how things deform and whether they're going to break or not when they're subject to particular loads in a tensile or compressive testing machine. And again, we can use some computer simulation when we start moving on to shapes that we can't use simple hand calculations to predict performance of. And this is a finite element simulation of the frame of our hand cycle as the athlete's pedaling. Materials and manufacturer, again, a very important part of the courses. And especially if you're looking at one of our composites pathways, the images on the left here will be of interest to you. So this was the manufacture of the body of our hand cycle. So first of all, CNC machining out of MDF to get the shape of the hand cycle. This is called a plug, the same sort of shape as we want the hand cycle body to be, which we then coat in a a special resin and polish to a high surface finish. We take a mold from that and then lay the actual hand cycle composite into that mold to produce the hand cycle shell itself. All sorts of other different materials that we'll be looking at as well in your materials and manufacturing modules. So CNC machining of metals here, and this is our water jet cutter, again cutting out parts for the hand cycle. Dynamics and control is really interesting and very important for both the submarine project and the hand cycle project. So the control of the control surfaces that are making the submarine go up and down, left and right, is actually remarkably difficult to get right. You may think it's straightforward, but we found out the hard way it isn't. And even the hand cycle, in this analysis, dynamics is all about how an object responds to forces imposed on it. So the motion that is created when you apply some forces to an object. And we were interested in things like what happens if there's a gust of wind hits the side of the hand cycle. Is that hand cycle going to want to return to the nice straight course that it was on before, or is it going to kind of veer off course, which clearly could be dangerous? We can use some control maths to work that kind of thing out. Electronics and electrical engineering increasingly inseparable really from mechanical engineering these days, and indeed marine engineering. So we worked with a company in America to work out an automatic gear changing system for our hand cycle. So we got parts there. And the other thing we had on the hand cycle was a data logging system, a much simpler version, but similar sort of thing as the kind of data logging thing that you'll see on a Formula One application, so that we can take out our hand cycle, do a load of tests, and work out how it responded to the power inputs, etc. from the athlete. Again, thermodynamics, another thing that you're going to see on your timetable, and you might at first glance wonder where thermodynamics could come into the design of a hand cycle. Well, if you look carefully, you see at the front of the hand cycle this little hole, and although it just looks like a hole in the hand cycle, there was actually a huge amount of maths went into the design of the shape of that hole, because anything that disturbs the surface of that aerodynamic shell is going to slow down the thing. It's going to increase the aerodynamic drag. So we want that hole to be as small as possible and exactly the right shape. But more importantly, we want to make sure that the heat from our athlete can escape. So the reason that hole is there is to ventilate the thing. We don't want to cook our athlete because when they're working hard, they're going to generate a lot of heat. So we can use some maths to predict how hot it's going to get inside there and minimize the size of the hole while still keeping our athlete cool enough. If you're on one of our marine programs, you'll certainly be looking at naval architecture. So this is looking at things like the stability of all sorts of different vessels and how to calculate that. Also the response of the vessel when it's in a seaway, a response to waves, and all the theory that you need to know about boat and ship design that then feeds into the design process that you'll look at designing special purpose vessels like the one that you see on the right here. That's some of our third year marine technology design work on display there. Marine students will also be looking at resistance and propulsion. So amongst other things, that's the theory of how propellers work. And here I've given the example of the human-powered submarine. So we've got it featured a contra-rotating propeller, so that one going that way, the other one going in the opposite direction with variable pitch blades. Unfortunately, you can't just go to a shop and buy a specialist human-powered submarine propeller. It has to be designed from scratch. Okay, and it's done with a thing called vector analysis. Okay, so that's some of the maths that went into the design of that human-powered submarine propeller there. And you'll have noticed actually that on pretty much every slide that we've seen here, has been some sort of formula or some sort of mathematical notation on each slide. And maths really is the key to unlocking all the different subject disciplines within engineering. So you'll study maths. I'm sure you already have studied maths to some degree. You'll study it to a greater extent. And maths really does come alive when we start seeing the power of it and the way that we can apply it into all these very interesting different subject disciplines. So once we have a little bit of knowledge in all of those different subject disciplines, supported by our mathematical knowledge, the really exciting bit starts, which is where we kind of put it all together. Okay, it's all very well being good at fluid mechanics or structures or materials and manufacturing, but what we really need to do is apply a little bit of creativity to be able to bring all those things together and actually design products. Okay, so this is a particular interest of mine, is mechanical engineering design or engineering design in general. And this is the sort of thing that students might start off in their design process, kind of defining a problem and then coming up with various different concepts as to how they might solve that problem, either with sketches or simple computer-aided design models, then working those up into slightly more polished computer-aided design models. So this is at the concept stage, then moving on, producing drawings for components, working out how they're all going to be assembled, and final 3D models of the thing that are going to actually be built. And this image on the right here is actually a 3D model of the hand cycle minus the aerodynamic shell, which was completely built on a computer before a single component was manufactured. So we knew exactly what shape everything was going to be, how much it was going to weigh, how strong it was going to be, how the athlete would fit in, before we started manufacturing anything, because it's very expensive to manufacture components and then discover that we've got them wrong later on. So that's an important part of the design process again. But just as important in the design process is actually the management of that design process. So managing our time with things like Gantt charts, managing budgets, finances, and also managing risk. I mean, obviously, a human-powered submarine and a hand cycle both involve some degree of risk. So we teach our students all the techniques that they can apply to minimize those risks to an acceptable level. So I hope that gives you some idea of some of the subject areas. By no means an exhaustive list of the subject areas that you will study while studying engineering here at Plymouth. And also how we use those subject areas in context with some of the projects. If you do have more information, please do have a look at our website. And if you have any questions at all, contact us. The admissions inquiries details are on the right there. Thank you very much for listening.